Hello students. In this video, we cover the last three sections of Module 7 on decision trees. And this is where it gets quite exciting because in those methods we're going to cover, bootstrap aggregation, random forest, boosting, we will combine many trees together and obtain models that are meant to be much more accurate in their predictions compared to um, standalone trees. Now, one thing to say is that in this video, we actually cover quite a lot. We cover quite a lot of very important ideas in statistics and machine learning, very powerful ideas, and we do that in a relatively short amount of time. So maybe have in mind that this is an introduction to those concepts. We want to communicate to you the main ideas, show you some R commands that you can actually fit those models in practice, but it's an introduction. Much more could be said about those methods. So let's get into it. Just to summarize a bit of advantages and disadvantages of trees, and here we mean trees as we've seen in the previous part of this module, standalone trees, so a single tree. So advantages, well, they're pretty easy to explain. Recall that in a tree, the structure is always at every node, you make a yes/no decision to choose which branch of the tree you're going to keep going down to. So that's quite intuitive to explain. This point is put in parenthesis. You could say maybe that it kind of mirrors human decision making because, again, at every internal node, you make a yes/no decision, and that is maybe how humans kind of think. Um, then yeah, you can display a tree as a single on a single chart that is again quite easy to interpret. Um, and you can a tree easily handles qualitative predictors. So there's no problem having qualitative variables. I mean that have a set number of categories, in addition to, of course, dealing with quantitative predictors. Disadvantages. Well, usually they will have low predictive accuracy compared to other regression and classification approaches, and they can be quite non-robust. So non-robust means um, if you get a different sample, even that is only slightly different, you might get a fairly different tree. And that's not very good. You might say the variance of predictions is quite high then, because um, even if the prediction is unbiased, like on average correct, if a different tree would be created by a slightly different data set, well, it means that the prediction is quite variable, which is, as you know, not good. So how can we improve the performance or predictive performance of trees? Well, we've already discussed pruning. So recall if you've obtained a tree that is very deep, as many leaves and few observations per leaves, that's a deep tree, you can prune it back. So from the big tree, you progressively remove some of the splits that you've made to create the tree, and that creates a model that is more well, parsimonious, and it could improve a little bit the prediction this tree would make on a test set. But this is limited. You still only have one tree. So what we discuss in this lecture is so-called ensemble methods. So ensemble methods, this is a very broad idea, broadly applicable in machine learning. So we will discuss it. We'll discuss three ensemble methods that each of them is quite broad as well, but specifically we'll discuss them for trees. But I suppose here I'm saying that many of the ideas we apply specifically to trees, they apply very broadly in machine learning and statistics in general. Um, so what do we mean by ensemble methods? Well, it's actually very simple. Um, we've seen already that, of course, to solve a specific problem, to complete a specific task, you might have many different models to do the same task. Here, well, it's an example for classification task. So you could have a logistic regression model to do that. Okay, SVM. This is for support vector machine, I believe. Another model we're going to cover in this course, but it's another model you can use for classification. In a few moments, we're going to present a random forest that you can use for classification, and so on. You could have a standalone tree. You could have other models. So each of them might give you different answers, right? Make different predictions for the category of your response. And so we've already seen that maybe you can have some methods to pick the best model out of these ones. Or in machine learning, usually this would be the error rate computed on a test or validation set, right? But now ensemble methods tell you pretty much why pick the single best one? Why not just put them all together and use all of those competing models to make your final predictions? So a simple idea, don't just pick the best one because they might all be pretty good. If they're all pretty good, why not just average out their results and that's your final prediction? So basically, for a classification problem, this would be what it looks like. Okay, maybe your first model predicts category one for a given observation. Model 2 predicts again category 1. Model 3, oh, predicts category 2, but then model 4 predicts category 1. So then you take a majority vote. 3 out of 4 models in this example predict category 1. You predict category 1, and so you've combined the results of many models to make your final prediction. And this is the idea of ensemble models. Don't pick the single best one, average out the results instead. Okay, now we see a specific example of that using Bootstrap. Now, Bootstrap is another of those statistical ideas that is very broadly applicable as many different applications. Uh, so we apply it specifically to create models from many trees. Each of these trees will be fit like before, but on what we call a bootstrap sample. Now, what is a bootstrap sample? I'll tell you quickly what it is, but then it's going to be easier to follow with a simple example. But simply put, um, a bootstrap sample is that you take your initial sample, but you mean all your data that you have, and you pick observations at random from the sample, but with replacement. So you pick one observation, you pick another one, but you can always repick the same ones from your initial data set. You do that n times if your data set has n observations, and you obtain a new sample. And on this sample, you can refit your model again. And if you do that for many bootstrap samples, you can obtain many models that achieve the same task, like a regression task or a classification task. And at the end, as we said for ensemble methods, you just put them all together and you average out the predictions. By average out, I mean if it's a regression problem, you literally average out the predictions because they're numerical, you can take the average. If it's a classification problem, by average out, I mean take a majority vote. The category picked the most often by all those bootstrapped model is the one that is your final predictions. Now let's visualize this with a specific data set here. I believe it's a fake data set. Not 100% sure, but doesn't matter what this data set is. We just want to explain here what we mean by a bootstrap sample. So on the left, you would have your initial data set. Now, so this would be, well, here x1, x2 could be two predictors, I suppose, or maybe x1 could be the predictor, x2 could be the response. It doesn't matter here. I just want to illustrate the idea of bootstrap, which is this. This is your initial sample. Now, to make it clearer what's happening, we arrange it by increasing value of the first variable, okay? Increasing value x1. That's not a necessary step for the bootstrap. This is just to help us visualize. On the right, we take our first bootstrap resample, which is this. From your initial data set, you're going to sample from it same number of rows. So if you have a sample here of size, the full sample seems to be of size 50 because here, you can view the other ones. It doesn't matter too much, but from a sample of size 50, we want to obtain a bootstrap sample of size 50 again. This is why the size is just the number of rows. And then what we do is we just use the option replace equals true, because in this sample n function, if replace is not true, you're just going to pick exactly the same 50 observation. That's not useful because the two samples will be totally identical here. But if you have replace equals true, it simply means that one observation can be picked many times. So you see, for example, and again here to help us visualize, we arrange by x1. So we have this bootstrap sample is in its ascending order of its x1 variable. So this first point is actually here in the second, in the bootstrap sample. But you see it's here quite a few times. It's actually here 4 times. So when we bootstrap by random chance, we have picked the first observation 4 times. But you see, the second data set, the bootstrap data set, also has 50 observations in total. So if the first one is 4 times, it automatically means that some of those observations will not be picked. For example, well, let's try to find an example of that. So 108 and 761 is here again. And by the way, here we're bootstrapping the rows, right? So it means if you add 1.03 here and 6.78 for x2, those are still attached, right? So rows are replicated, but they're not shuffled, right? So that's actually quite important. So here, yeah, the 1.03, 6.78 will always be also here, 1.03, 6.78, and so on. But now my point is just this. Let's look at this one. Okay, it's here again. 185 is here again. Okay, well, actually, okay, we need to find an example that's not there. So let's see. 204, is it there? We don't see it on the first page, and it's not on the second page either. And remember, this is ordered by X1, so it means this specific point, 204, 1, and then 192 for X2, is not present in the bootstrap sample, okay? And this would be true of other points as well, like, yeah, 257 is not in the bootstrap sample. So essentially, again, what we do, initial sample, we take at random all the observations from the initial data set, but they can be then replicated. So and the way you can view this is simply when the first data point for the bootstrap sample is chosen, you have 50 choices. Because you have 50 data points in the first or the initial data set. When you sample the second point, you still have 50 choices. So you could make twice the same choice. Third point, you still have 50 choices. This is what we mean by sampling with replacement. And so how do we use this idea of bootstrapping different samples to create a more powerful tree-based method? Well, this is what we do, bootstrap aggregation. So bootstrap aggregation, bagging for short. Okay, so it's a general purpose procedure to reduce the variance of predictions. So yes, this should reduce the variance of our predictions and hence also reduce their overall, prediction error, mean squared error. So that's good. Okay, so it's broadly applicable, but it's particularly useful in the context of decision trees. So let's explain specifically for trees. First step, bootstrap. So as we said, you resample with replacement the original data set many times. Say, okay, in general, we're going to call this big B, the number of different bootstrap training data sets you could have. This, I think typically this would be several hundreds, even maybe 1,000, or even several thousands. Just as a side note, for bootstrap aggregation, it's not that critically important how many bootstraps samples you have. Like, it's not a parameter that is vastly important. Basically, you just need it to be high enough that you achieved a good level of reduction in variance. But my point is just, there's no problem with having it very large. You're not going to overfit just because it's very large. Okay. But anyway, that's a side note. Once you have, again, many resamples of your initial data, you train a single tree on each of those data sets. So on the beat bootstrap training set, you obtain a tree and you don't have the concern to prune it. That doesn't matter if this tree is very deep, because you're going to average out many trees. No, there's no point in pruning, or no specific benefit in pruning. And so on this specific tree, so you train tree 1 on sample 1, tree 2 on sample 2, and so on. So you get different predictions. You get different models, basically, one tree per bootstrap sample. And again, a tree is, as we've done before in the first part of this lecture, meaning you have a regression task. Your tree is splitting the data at relevant points based on minimizing the residual sum of squares to try to decide in what leaf each observation should be categorized. And then once you have built your tree, you can make a prediction about a data point that is not in your initial sample. But now the last step is that you aggregate all your fitted bootstrapped trees. So you take the average prediction if it's a regression problem. So if your response is quantitative, every tree you fitted can produce a prediction for any uh, out of sample predictor value X. So your beat tree will produce the prediction f hat bx, but you want the final prediction, and this is simply the average over all those fitted trees. Okay, an example of an ensemble method. You've created many, many, many models. You take the average to be your final prediction. If this is a classification problem, well, it's very well. There's the same idea, but instead you take the majority vote. So again, for a given x, whose response you want to predict, but now the response is categorical, what you do is simply you choose the most common category predicted for that specific x by your B models, your B trees. And yeah, and so conceptually, that's a way to reduce the variance of your trees because hopefully this point was clear, but let me make it again. Your first bootstrap sample will be somehow similar to the overall training set, but it will be a bit different because you've sampled some observation and some observation a few times and some observation none at all. So this data set will create a tree that will be a bit different or maybe even very different than the second data set because the second data set, although it comes from your initial training data, will be a bit different. Random chance will have taken some observations out, some observations will be there a few times. So this tree will be a bit different, this tree will be a bit different. So it's a way to create many, many different models to achieve what to perform the same the same task, get a prediction. But then if you average them out, you should reduce the variance because yeah, usually the average of a quantity is less variable than any individual points itself. So in this example, well, the average prediction from many models should be less variable than a single prediction from a single model. So let's illustrate that here. Okay, this is a classification example. So imagine those would correspond to 8 bootstrap samples. So again, you start with an initial data set here of 2 predictors, x1, x2. Oh, this might actually be, this is probably this actual data set here. But anyway, you bootstrap it, in this case, 8 times. Each of those samples can be used to fit a classification tree. Here, the classification task is that, well, the response can take only 2 categories, blue or green. And so here, what the first plot is showing is one fitted tree for this specific bootstrap sample. Recall what we show you here is the final leaves, the final regions. Because of course you could represent each of these trees by a literal tree, but you can also visualize it here at least if there's only 2 predictors on this scatter plot, meaning first predictor here, second predictor here, and those rectangle regions are the leaves, meaning in this region, the top one, every point is predicted to be, any point in this region is predicted to be blue. In this region here, any point is predicted to be green, and so on. The second bootstrap sample has different predictions. So here you have, well, in this region, the point is predicted to be green, and so on. Now, from those bootstrap samples, conceptually, how do you obtain your final prediction? Let's just make one example. Suppose I want to, well, actually, I'm going to ask you to do it in your mind, and then I'm going to explain. Suppose I want to predict the category of a point with value x1 equals 6 and value x2 equals 9. Okay, so again, your goal now is to find the prediction that this bootstrap method would make of a point that has x1 equals 6 and x2 equals 9. Take a moment to see if you can figure it out based on this data here. So now the solution is you need to check each of these 8 predictions and take the majority, right? So quickly, okay, the first plot, if x1 is 6, x2 is 9, we're in the blue region, so we predict blue. But the second, we predict green. The third, we predict green. This one we predict blue. This one we predict green. This one we predict looks like we predict green, yes, green and then blue. So out of 8, we predict 5 times green and 3 times blue. Okay, green wins. Final prediction is green. Okay, this is a tree. Maybe I should have presented this before, but this is a tree representations of those 8 samples. I don't think here I have the patience to analyze all of them, but you can take a moment to convince yourself that those trees corresponds to those depictions here. I mean, we can do the simplest one is the last one because there's only one decision node. X2 bigger or equal to 4. So if yes, we're bigger than 4, we predict blue, correct? And if we're smaller than or equal to 4, we predict green, so we're here. Okay, so now here, I suppose this is a bit of terminology in the bag or out the bag, which I find slightly funny. But anyway, um, let's say element ij of the matrix is 1 if the ith observation is in the jth bootstrap sample. So then in that case, we say it's in the bag. Okay, that's a bit that's a lot of words, but we just mean okay. The rows here they represent the unique observations of the initial data set, and the columns represent the bootstrap bootstrap data set. So we're simply saying, okay, the first observation here there's a 1 because it is in the first bootstrap sample. It is not in the second, it is in the third, it is not in the fourth, and so on. Okay, and again, for the second row would mean the second observation of the initial data set. Okay, it is in the first bootstrap sample, but it's not in the second, it is in the third, and so on. Okay, because again, central idea here, from the initial data set, each observation will be in some of the bootstrap sample and not be in some others. Here you have the opposite idea, so exact opposite. This is what we call out of the bag. Out of the bag, so element ij is 1 if the ith observation is not in the jth bootstrap sample, and this is called out of the bag. So okay, so this matrix is the total opposite of this one. The first observation was not in the bootstrap sample number 2, so here you have a 1 to signal that it was not in the bootstrap sample number 2. But now there's another column here. This is the number out of the bag, right? So for the 5 first bootstrap sample, the first observation was out of the bag 3 times. So it was not in 3 of those first 5 bootstrap sample. The second one was not there 3 times, blah, blah, blah. Now, the key point is if you have many bootstrap sample, like more than 5, for example, it is essentially guaranteed that every observation will be out of the bag many times. So here we just have 5, so the first one is out of the bag 3 times. We still get an observation here that is never out of the bag, like observation 9 for some reason is present in all the first 5. But I hope you see that if you keep bootstrapping, eventually, well, observation 9 will be out of the bag for at least some of the bootstrap sample. Now, why does that matter? Why are we explaining all this? It's simply that out of the bag observations give you a very nice, very neat, very clever, I would say, way to compute cross-validation error. And you basically get cross-validation error for free in Bootstrap model, which is quite nice. So you don't need to do an additional step of cross-validation. You get cross-validation for free. What do we mean by that? Let's review the slide, which is actually called out-of-bag error estimation. So you can do the maths. On average, each bagged tree makes use of around 2/3 of the observations. Okay, so the maths, I don't think this is too complex to show, but on average, if you resample, if your bootstrap sample has the same number of observations of your initial data set, you get 2/3 of the observations will be used. Let me rephrase. In any given bootstrap sample, on average, 2/3 of the initial data are there. which means, though, that on average, 1/3 of the initial data is not there. So 1/3 of the observations are out of the bag. So what we can do to predict, to compute the test error is that for any response, for any observation, okay, so for any observation, we can predict the response using all of the trees for which that observation is out of the bag. Well, yes, as we said, any observation, if we have many bootstrap sample, will have some number of fitted trees that did not use that observation. Now, if a given tree did not use that observation, it means we can use that tree to compute a prediction of that observation without danger of overfitting, because that specific tree did not use that observation. Recall, the danger of overfitting is that the model can kind of follow too closely the points it's using as a training in the training process, and that results in overfitting. But for a point that is out of the bag, the tree has never seen that point, so there's no trouble there. You can compute an estimate of the error that will not be biased, again, because that tree has not seen that observation. I don't know if that idea makes sense. Hopefully it does. So indeed, what you get is that for every observation, around 1/3 of your trees did not use this observation in the fitting procedure. So you can use around 1/3 of your trees to make a prediction whose error will not be biased, and that's quite nice. So what you do is you take the average. Okay, for a regression problem, you take the average. For a classification problem, you take the majority prediction to obtain the final out of the bag prediction for the ith observation. So again, let's just take an example. Fix some numbers. Let's say you have 1,000 trees. So for every observation, you'll have around, on average, 333 trees that have not been trained with that observation in them, in the fitting. So you take those 333 trees, you predict what the response should be for that ith observation, and you average them out. And with this, you get your final prediction that you use to compute the error. Because you know the response for this observation. So you take as usual, the response minus the fitted value, the prediction obtained from those 333 trees in my example. Take the square and you get your error for that. You squared error for that observation. You do that for every observation, so you get your mean squared error, and that is a roughly unbiased estimate of your mean squared error for your bagged tree model. Okay, and the authors of our textbooks will tell you would be sufficiently large, out of bag error is virtually equivalent to leave one out cross-validation error, but leave one out cross-validation would be very computationally expensive. So especially for bootstrap samples, because we need to fit the tree like 1,000 times or something like that. So it's pretty good that we don't have to do that because of this nice idea of out of bag error estimation. Okay, now, so bagging is a pretty powerful idea. Now, we do get the downside that bagging can lead to difficult to interpret results because now, you don't have a single tree, so you don't have this nice structure that you can visualize clearly because you've averaged out the predictions from many trees. But there's at least some way to still have some sort of measure of overall how important are each of the predictors on average in all those trees, and this is what the textbook will tell you. You can compute the importance of every predictor. There's at least a few ways to do that, but the one they suggest in the book is, okay, if you have a regression tree, you can record the total amount that the RSS, residual sum of square, is decreased due to splits over a given predictor, average over all B trees. So so you recall that the way one tree is fit is exactly with RSS. You pick the splits that minimize the reduction in RSS. So for every predictor, in a given tree, you can find by how much the RSS has decreased by the fact that you've used that predictor to make your splits. you can do that for a tree, but you can do that for that specific predictor. You can check the reduction in RSS on all your B trees, and then you take the average. You take the average reduction for every predictor, and that's some measure that of the importance of sorry, the importance of any predictor by how much they've decreased the RSS, uh, well, compared to other predictors. And for classification trees, same idea, but instead you compute well, for example, the Gini index, or I suppose you could use the entropy. By how much does the entropy decrease when you use a given predictor to make your splits and average over all the B trees. Okay, so we're done with bootstrap aggregation. So this is the first method to well to improve our predictions by putting many trees together. Okay, so just a word in general, random forests are a tweak, if you will, to bootstrap aggregation. So random forest, I don't think I'm going to spend too much time on it. It's really just like bootstrap aggregation, but we change one detail. So it's a very similar idea, just one detail change. But then boosting is a pretty different idea. So in your mind, you should have that, okay, bootstrap aggregation and random forest are not necessarily similar in the results they yield. Okay, not necessarily similar in the results they yield, but conceptually similar. Boosting is a different idea. But now, first things first, random forests. Okay, so now you have a forest here. I don't know if that's useful. I mean, maybe if you've never seen a forest in your life, maybe that's useful. That's what a forest is. Whether this is a random forest or not, I'm not too sure. But for us, random forest has a specific statistical meaning. So let's review what it is. And I suppose the motivation comes from maybe an issue you can have with your bagging. Bagging tends to produce very correlated trees. By correlated, maybe it will be a bit more precise to say that yeah, the predictions they produce are quite correlated. They will tend to be, suppose they will tend to be quite similar. And so and this I suppose is a general point, but in general, yeah, if you average out quantities that are strongly correlated, the reduction in variance is not as big. If you average out quantities that are very independent or close to being independent, less correlated, the reduction in variance you obtain is much greater. I don't know. I suppose this is more an analogy than a direct application, but yeah, you get more diversification by having independent quantities and putting them together, right? If you invest, you would like to invest in assets that are not correlated to each other, because then yeah, you will get a smaller variance for your average portfolio, and smaller variance investment is good. If all your It's actually a good example. Yeah, if all your assets are very correlated, well, overall, the variance of your portfolio will be big, and the variance of portfolio is bad because it means your results are very variable. Yes, you can make a big profit, but you can make a big loss as well. Anyway, enough of that sort of dubious analogies. How do we decorrelate our trees? Well, let me explain. Let me read what's there, and then let's explain if it needs explanation. So in random forest, the only tweak we make is that we will build our trees. Like single trees are grown just as a single tree was grown in the first part of this lecture. But now we make an important restriction in random forest. Whenever we decide that a new split is created, recall that you always split one predictor at a time, right? So, but when we make this decision about which predictor to pick to make the split, we are only allowed to use one out of m randomly selected predictors to make the split. So in a random forest, for each tree that we grow, at any step, when we decide to make a new split, instead of having p predictors to choose from, which is in general what we have, we randomly pick m out of those p, and then we say, okay, we can only make a split based on those m. And those have been chosen totally at random. So we pick completely at random n predictors out of p. we restrict ourselves to those m, and then among those m, we pick the best split. Best split as we did when we grew a single tree. Okay, that's the idea. But now, to be clear, at the next split, so once we've made one split in our tree, the next split, same thing, but we pick a new, completely random set of m out of p predictors, and only according to those m can we make a split. Okay, so that might sound a bit weird. Why do we restrict ourselves so much? The idea is written here. In general, strong predictors, okay, if you have predictors that really are better at reducing the RSS at the very first step of growing a tree, they'll always be picked in bagging. They always be picked. So in your bagging, in your bag trees, if you don't put any restrictions, the first split will always be the same pretty much if you have one strong predictor that is that's stronger than the others. So you see, this is going to create trees that are very similar to each other because they always pick the same predictors in the first few steps. So if we restrict the predictors on which the splits can be made, we let the other predictors, the one that are not so strong, at the first step, we give them the opportunity to have their effects captured by many more trees. So we kind of force the trees to be more different in some sense. And okay, this is not very formal language, but the smaller guys also get their chance to shine. Yeah, it's not always the first stronger predictor that is picked as the first split in the tree. And I think why this might help your trees is because remember that the method to build one single tree is greedy. It's greedy. Recall we explained this means one split is always chosen to be the best, but at one specific step, at one specific point in time, if you want. It's not necessarily the best split overall. So if you force some split to be made on predictors that would not be chosen without restrictions, maybe you're going to create trees that down the line are actually going to be better. Maybe. But overall, mostly you're going to create trees that are more different to each other. If they're more different, their predictions will be less correlated, and the overall variance of your final prediction might be lower. At least that's my explanation. Okay, now we said we're going to pick m out of the p. What m? I don't think there's a single best answer. A common choice is to pick m square root of p. So you see, m is substantially smaller than p. So if you have 100 predictors, at each step, you can only make a split based on 10 predictors. But I suppose other choices are possible. Now, just as a comment, you could say bagging is a special case of random forests. Yes, when you think about it, m in general, m can be whatever. So if you pick m to be p, well then you no longer have a restriction because at any step you can pick any predictors, and you fall back on the case of of bagging. Okay, this is the example from okay, so this is the flood insurance example. So the response was amount paid on building claims. We use all the predictors here. We use the training set. Okay, this is actually quite, I think it's relatively computationally expensive to do that. So we're just using 50 trees here. In reality, you probably use more than that, but I think to create those slides, we didn't want this to take all night to compute. But anyway, we use 50 trees. Importance, I'm going to explain that in the next slide. And here the point is just, we already had checked for a linear model that I believe I'm pretty sure this is the validation. This is a validation root mean squared error. So we set aside a validation set. So those estimates should be relatively unbiased. And then, yeah, okay, here random forest is so far the best. Okay, that's the lowest root mean squared error. We don't have bagging for some reason, but okay, anyway, random forest beats prune tree. Okay, and this is okay, so by the way, we're using the package random forest that I believe has this function importance, and this is computing what I explained, that you lose some interpretation when you bag your trees, but you can at least compute the importance of each of them. This is what was explained here, that you record the total reduction in RSS. Now, frankly, in the interest of time here, I'm not going to explain this in too much detail. You have two options. Those are two different ways to compute the so-called importance. So essentially, you're aggregating overall on average based on all the trees, how important is every predictor. What is described by the textbook here, uh, pretty sure it corresponds more to what is called node purity here. So node purity would be, yeah, what the textbook describes, yeah, overall average reduction in if it's a regression problem, root mean squared error. Uh, um, if it's a classification problem, Gini index. You also have the decrease percentage, percent. Okay, this is kind of the opposite. The percentage increase in MSC if you remove that predictor, right? Now, those two criteria, they yield they can yield different the different measures of importance. But here, yeah, I don't think I'm going to get into the details of each of them. But just you have some way to find out, kind of globally speaking, how important is each predictor on average in your back trees or random forests. And you see, yeah, those two things, they yield pretty different results. You see total building insurance coverage based on this node purity one is, you know, the highest by far, but then it's only kind of middle in if you use percentage increase in mean squared error without that predictor. But anyway, I'm not going to focus on that. Okay, we're at the last section, boosting. Boosting. So a new idea here. Yeah, I'll say again that boosting in general, in statistics or machine learning, pretty powerful idea. Um, Very quickly, what it is overall is if you fit a model and um, your residuals are poorly behaved. In general, it means that your model is somehow misspecified. It's not capturing all the trends in the data because there's still a pattern between your residuals and your predictor. So uh, in general, pretty much any model makes the assumption that the residuals are independent from the predictors. They're just a random noise as function of the predictors. So if your residuals are not well behaved like that, in the sense that there's patterns remaining between your residuals and your predictor, yeah, your model is not capturing everything in the data set. But the idea of boosting is that take your residuals and fit a new model to the residuals themselves. Residuals that the residuals are now viewed as the response as function of the predictors. And then you have a new prediction. Yeah, a new prediction, a new model that fits the residuals to the predictors, and you add that predictions to the initial fit of your response, and this is going to improve the fit of your response. And if that still doesn't work, if your updated prediction still has residuals that are poorly behaved, you do it again. You fit your residuals again, and you add the fit of those updated residuals to your initial fitted response, and that should improve your model. And you can do that basically many, many times until your residuals are well behaved. Okay, now this might sound a bit esoteric. We'll illustrate this at the end of this slide with a kind of simple example. But so let's first review the blah 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 that is written there, and then okay. So we have blah blah blah. We have a bit of algorithm, step by step to do this with trees, and towards the end, yeah, there will be this example that should. Maybe we should have started with the example, but no. Let's review the content and present the example at the end. That might help. Okay, so as I said, very general approach that can be applied to many statistical learning methods for both regression and classification. Okay, we focus on boosting for regression trees. Now, important to note here, this method also combines a large number of trees, but conceptually there's a big difference. The method does not rely on independent bootstrap samples. You see, in bootstrap samples, all those data sets that are bootstrapped, they're independent of each other. Like the first bootstrap sample aside the fact that it comes from the same data set, is independent of the second. Like there's no, if I know the first bootstrap sample, it doesn't give me additional information about the second one because the second one is, yeah, independently sampled from the initial population. Now, instead, in boosting, trees are grown sequentially, but so each new tree is created using information from previously grown trees. So those trees, each new tree is meant to improve the prediction overall. So it depends on the previous tree. So you see, that's quite different than boosting because, sorry, that's quite different than bagging because in bagging, you make independent predictions and then you average them out. In boosting, each prediction is an improvement from the previous one. So you see, conceptually, it's quite different. Now, each tree is fitted on a modified version of the original data, namely the updated residuals from the previous model. So again, conceptually, at each step, we want to improve the residuals. So make the residuals to have less and less patterns, which means that our prediction is better and better. And we do that many times until there's nothing left to model in the residuals, until our residuals are truly a white noise, no more patterns there, no more relationships between the residuals and the predictors. Like we've extracted all the information we could from those residuals. Now, by fitting residuals, at each step, the method specifically targets areas where the previous tree did not perform well. Yes. And unlike for standard trees, boosting enforces what you call slow learning. So yeah, that's another idea, I suppose. We will force the model to learn slowly. Now you might say, why? If the model learns too quick, it might overfit. So by forcing the model to just make tiny improvements at each step, we kind of prevent that it's going to make too big changes that might actually not be not be correct, overfit in the sense that you start fitting the noise rather than the real trend in the data. Okay, now the algorithm, then we apply to our example of the insurance claims, and then we present a toy example to make all of this a bit more concrete. Okay, what is the algorithm? How do we do this? What is this boosting more specifically? So first of all, you will set your overall prediction to 0. Okay, so you set it to 0 to begin with. And now, in terms of notation here, careful, f hat will be what I want my final model to be, what my final prediction of my response based on the predictors x. Now, if you start with your fitted values at 0, it means that your residuals are simply y, the response. Well, yes, because residuals is response minus fitted. Well, if the fitted is 0, response minus fitted is just response. Now, you do many times the following three-step ABCD. Okay, so for B goes to 1, 2, up to B large numbers, you do all those things. Fit a tree. So careful here, now we have the notation f hat B to mean the beat instance here. So fit a tree with D splits okay, so recall, if you have D splits in your tree, it means you have D plus 1 leaves. Leaves are also called terminal nodes. But here you fit the residuals. Okay, so you fit the residuals, and so you're going to fit your residuals is now the response, and you fit it using the predictors, well, X. Now you fit your residual, and you use those new fitted, well, yeah, you use the fit you've made on the residual to improve your prediction of the actual response. So now you update your f hat, the one you had over there, by adding a shrunken version of the new tree. So to enforce slow learning, we don't want the model to learn too quickly. We add only a small portion of the fitted residual, and that is meant to improve our prediction of the actual response. So we take our initial value, but at the very first step would be 0, but it won't be 0 any other step. We add the residual, well, the fitted residual, I mean, but only only a shrunken part of it. Then we update the residuals, and same thing. The residuals are only slightly updated, so we take, because recall, now the residual are our response that we fit. We fit with the tree model, so our fit is now f hat b. Now the new updated residual will be the new response that is the old residual, to which we subtract the prediction made by the model. Okay, so again, it's like this is like response minus residual, um, but the shrunken residual. This is why there's a lambda in front here. Okay, now again, the idea is this. I'm improving my f hat, but very slowly because at each step I'm adding a small portion of my fitted residual. I do that many times, and eventually the residuals are no longer, there's no longer patterns there. They're basically, it's not changing the residuals to fit them again. Well, it's not changing them meaningfully to fit again based on X, and I stop. I stop, and that's it. Now, so yeah, so after I've completed step 2 many times, b times, the final boosted model is just the last iteration of f hat, because here again at this step, well, at each time I compute this, I'm updating my f hat. Once I finish this step, once in programming terms, you would say once you exit this loop, well, the last iteration of your f hat is your final prediction. Now, you might note, in fact, f hat is just the sum of all the lambda f hat b. Well, yes, because, well, convince yourself this is true. You started at 0, so then each time you just add this quantity, overall, you'll have just this sum. Okay, so that's the algorithm. Now, a few comments. You might have noticed there's quite a few arbitrary choices you need to make. So I think fair to say the most important one is the choice of trees, because that's actually important. Unlike in bootstrap or trees, bagging, so unlike in bagging, if B is too large, you can overfit. Well, yes, because if B is too large, it basically means even once the residuals have no pattern with the X, you keep fitting them. So you keep fitting them, but if they have no real patterns, you're going to start finding patterns that are only noise, and that will lead to overfitting. So meaning your model will not perform as well as it can on a test data. So yeah, so B too large can lead to overfitting. This is why I believe B is the most important parameter to kind of fine tune. Like in your data, you need to check that your B yields the best results possible. The other two things you need to kind of arbitrarily choose is actually the shrinkage parameter. This is typically a pretty small positive number. I'm not, to be honest with you, I'm not sure if it matters that much what it will be, but typical choices are 0.01 or 0.001, like a tiny quantity. And also something else you need to choose, but I suppose you could try for a few different lambdas and for a few different Ds and see if your test mean square error changes, I mean your validation, your mean square error on the validation set. So yeah, the D is the number of split at each tree. But now typically, because in a way we want the model to learn slowly, it's okay to pick D small. So typically you pick a D of just 1 or 2. Because again, you're going to do that many times anyway, and you force your model to learn slowly. So to have trees that are simple at each step is fine. Okay, so this is our example from before. To do boosting, you need this package GBM. GBM stands for, I think it's generalized boosting models, I think. Okay, so a relatively simple syntax. Again, you start with your response. Here we fit it on the whole data set, so it's just tilde dot. Okay, we try this on our training data. Distribution equals Gaussian. don't be confused by this. We're fitting a tree, so it's not like we don't assume anything is normal here. Distribution equals Gaussian here has only the effect of having our criteria to build the trees be RSS, a residual sum of squares, right? Just predictions, sorry, value minus prediction squared, okay? That's all distribution equals Gaussian does. Okay, we're gonna have 5,000 trees here. Interaction depth 2, so each given tree doesn't go very far. It just means I believe our D here would be 2. You could try with 1 as well or 3, but I'm guessing with 3, if 500 trees, maybe you'll have it's gonna take a long time to fit. I haven't tried, but and shrinkage. Okay, so this is our lambda 0.01. For cross validation, so this is gonna do a cross validations for you. So you can pick the number of folds here. 5 is a default, common default. And here we get the results. So let's just interpret them. Okay, our best iteration is again because number of trees here 5,000 corresponds to the B here. But what I told you is that there's the danger of having a B that is too large where you start to overfit. And here this chart is actually making this point. The green line is the cross-validated. Okay, it's the cross-validated mean squared error. And you see, I guess it doesn't increase like crazy, but it does increase a little bit. Okay, so once B gets too large, you stop improving your cross-validated error, which means a B here close to a bit smaller than 1,000 is the minimum, apparently the minimum cross-validated error. And now I believe the black line is the error on the training set. And you see the error on the training set keeps decreasing. But as we said many times in the course, error on the training set is not the best criteria to use because, again, you can always overfit the training set. Okay, just a summary. We've tried many models now. For this specific, for the specific example of the flood claims, boosting doesn't perform well. I would say it doesn't perform well at all because even the large tree predicted had a smaller validation error. So sorry, I don't have a good explanations for this. Could happen for specific data sets. Any given method is never guaranteed to yield the best results. Here we still had our final winner is our random forest from before. By the way, here I don't know why it's displayed a bit weirdly, but this means 4.28 times 10 to the 4. Okay, so this means a root mean squared error on the validation set of 42,800 blah blah blah. Oh, and lastly, I'm not going to review this, but this is just computing kind of the final estimate of the error rate, root mean squared error here, computed on the test set. So somewhere in the code that you can find on the website, at the very beginning, we set aside the test set. So at the end, if we have many different models and we want a approximately unbiased estimate of the test error, you need to compute that on the test set. And this is what is done here. You see it's slightly higher. 44,000 is slightly higher than the value here. Okay, now final illustration of boosting in practice, okay, with a small example. So this was the small example where you have only one predictor here on the x-axis and the response on the y-axis, and you see it's a kind of a non-linear data set here. So at the first step, the residuals are literally your responses, right? Because recall, well, this is what we said before. At the first step, residuals equals the response. So what is displayed here is exactly this. Your residuals are your responses, the blue dots, and you perform your first fit. Okay, so again, if you look at the algorithm, first time you're going to fit a tree. With D splits, here we're going to have only one split. So we pick D equals 1 to your training data, and the training data is the residuals. Residuals, you fit them using X, the only predictor in this case, only one predictor. Okay, so this is what is illustrated here. The first tree, of course, we fit a tree, and the first tree find a best split at this point here. So now we're going to fit all the data points before this tree are going to be fitted with this value, and all the data points after the split are fitted with this value. So we fitted our residual. Now, second step in the algorithm, or I suppose this step called B, I suppose. So yeah, B. update f hat. Okay, so you will update f hat. You take your initial prediction. At the very, very first step, your initial prediction is 0, and you add your shrunken um, fitted residual. So what does it look like in our example? Well, here to make things visualizable, we're not going to use a super small lambda. Okay, we want to visualize what's happening, so we're going to use a lambda of 1/2. So it means that this on the left, the green line is our fitted residual, but we're only adding to our initial predictions off of it. So you see, our initial prediction was just 0. So we're going to add to it off of this green curve, so we get the purple curve. You see, here we had a height a bit below 4. We add to 0 off of it, so we get a line a bit below 2, and so on, right? Here we add a bit more than 1, so we get something a bit smaller than 1. Okay, so that's the first time we update our prediction. But you see, conceptually, you start to do a little something. Here, our prediction is, okay, not great, but it's better than predicting 0, the thing we started with. And then we update the residuals. Okay, so that would be step C. We update our residuals. We take the previous residual, to which we subtract the shrunken version of the fitted residual. Okay, so same thing. Well, same thing. We take our residual, we subtract to it the off of the fitted or the fitted of their fitted values. We get the new residuals on here on the right. Then we do it again. The new residuals, okay, in at the end of first step, we display them at the second step on the left panel. Okay, so here the points that are here, they were the same as were here. And now we fit them again to the predictor X by a simple tree, a tree with only one split. And now apparently the algorithm has found that the best split is here at the value a bit before 2. And then what's the next step? Well, we have a new fit for the residual. We add it to our prediction for the response. So we add it. So we add a shrunken version of it. We add off of this green line to our previously fit. So you see this purple line, we add to it off of this green curve. This is what is the result. Try to convince yourself that's true. Well, yes. Before we had this was flat at around a bit smaller than 1. Now we add here, we're going to add for high values, we're going to add the off of something slightly bigger than 2. So yes, we're going to get a value that is now over here, and so on. And then you keep going. Now, again, you update your residuals. And you see the point is that as you progress, your residuals, they get less and less meaningfully related to the predictor. You know, in the first step here now, the new residuals still have some pattern. In the next step, okay, there's still a pattern that has diminished, but then you keep going. You fit the residuals again, you update. On the middle, you update your predictions for the response. And on the right, your new residuals get more and more kind of flattened. There's less and less pattern between the residual and the predictor, and that's good. You grab more and more of those patterns in the residuals, and you update your predictions with those patterns, and you improve your model because you make you make the residuals more and more behaving like a white noise, like a cloud of points around 0. You keep going. I'm not going to review in detail the other ones, and then the point is that the prediction, you see the middle panel, gets more and more finely tuned to the actual data points. It gets better and better. And your residuals get more and more flat, more and more like a cloud of points with an average of 0. And that's it. Now, at the fifth step here, probably it's still not amazing. Like the residuals are there's still a little bit of a curved shape, but look at those new residuals in step 5 versus the residuals you started with. There's way less pattern there, and your prediction is better at step 5, of course, than it was at step 1. Okay, illustration here on a simple example of this boosting idea. Hope you followed me along. But I know that those are lots of new ideas. I've tried my best to explain them in a relatively short video. So obviously, if you have questions following this, you can send them my way. Okay, the last slide, I don't even think I'm going to cover it. I think this is more for your information. You can review in this book. They talk about this. Okay, I'm going to say one thing. If a certain orientation of your predictors doesn't, how to say, the orientation in space of your predictors might affect how well trees are going to perform. So in this a simple example on the left, if your data is like a square like that, and all the red are on the left and all the blue triangles on the right, a tree with a single split will perform extremely well. This data, if you rotate it, and now you get your square is now a diamond, it's going to take you way more splits, at least one more in this example, to get to the same very good fit. Okay, but that's really more of a side note that I leave you with to ponder or not. Okay, so I'm done. I think this video is long enough, so I'll stop here. Again, thanks so much for watching. Hope to see you in the next video or in class. Although attendance in class these days has been a bit I don't want to say abysmal, but I understand. You're very busy on a Monday morning. Anyway, I'll stop here.